Okay, here's the beginning of chapter 8, 8.1. Talk about sets. Sets essentially are like paper bags that you have stuff inside. It has material inside, it has elements, it has objects. In this setting, we're talking about numbers and letters. So we take a collection of objects, which we call, for us, we're in math, so mostly numbers. We do some words and letters, but mostly numbers. These braces are like parentheses bent. They're what the sets are inside of. Elements are members, objects. They're the things that are inside the set, like numbers and letters and that kind of thing. This weird looking E thing, it means is an element of. It belongs to the set. With the slash through it means it doesn't belong to that set. So is belongs to the set, does not belong to the set. Is an element of, is not an element of. It's just notation for right now. There are essentially multiple ways of writing a set. You can list everything in words inside of braces, or you can have this notation. It's actually called set builder notation, where essentially it is the set of all x's, the set of all x such that x is something about x. That's what this represents here. And then you have the empty set. You have a paper bag essentially with nothing in it. So either empty braces with nothing inside of it, or this null set, this little zero with a line through it. It's null set. So the empty set or null set means a set with nothing in it. So just the idea here. Let A, capital A, be the set of 1, 2, 3, 4, 5. So this set has 5 elements. 1, 2, 3, 4, 5. This is the set with A, E, I, O, U, which essentially are the vowels in the alphabet. C is the set with a cat and a dog in it. 4 is a set with Texas, California, and New York in it. 5 is a set of all x's such that x is an even number, like 0, 2, 4, 6, 8, -2, -4, -6, -8, all the numbers that are divisible by 2, even numbers. And then number 6 is a set of all x's such that x is a student at STC. All the students that belong to STC belong to this set. 7 and 8 are the empty set. It's like this, but with nothing inside. We call that the empty set. This symbol here is another way of writing a set with no elements. Okay, so these are just some examples of how you would write set. 1, 2, 3, 4. Essentially, and actually well, 7 and 8 also, I guess, but in a weird way, just really the first 4 are more like listing notation. This really has nothing to list, 7 and 8. And 5 and 6 are set builder notation. But if you take a set D, that's the number that has a set 2, has the elements 2, 4, 6, 8. Essentially, 2 belongs to this set, 4 belongs to this set, 6 belongs to this set, and 8 belongs to D. So this means they're elements of. In this one, A, B, C, D, E, the letter F does not belong to E, set E. 2 does not belong to set E. C belongs to set E. D belongs to set E. A belongs to set E. And B belongs to set E as well. And little e as well. So just nothing to solve, just notation, vocabulary. 2 sets are the same, equal, if they're exactly the same. They actually have the same number of elements, or the same elements are in both sets. They're not equal to if it has a line through it. And in fact, otherwise they're not equal, meaning if one has some element that the other one doesn't have, they're not exactly the same set. So equals, not equal to. So number 1, again, nothing to solve for here, but the set with the number 2, 4, and 3 is the same as the set with number 3, 2, and 4. They have exactly the same elements. They both have a 3, they both have a 4, they both have a 2. Neither one of these sets has something else that the other one does not have. So they're equal. 2, they're clearly not equal because the second set has a 3 while the first set does not. So they don't have the exact same elements, so not equal. A, B, C, D, D, C, B, A. Same 4 letters. Different order, but the same set. And then 4, A, 2, 3, triangle 4, 3, 2, square 6. Completely different, essentially. They're not exactly the same. So not equal, equal. Not equal, equal. Essentially, just notation, just definition, just talking a little bit about what sets are and how they work. Then you talk about what's called a set operator. There's many operators, but here we're going to look at a subset, and we're going to look at proper subset. It almost looks like less than or equal to and less than. So it kind of similar to numbers, but a subset is this symbol, kind of like with a little C and a little equal in the bottom. So kind of like a little C looking thing. If every element of A is also an element of B. So the first set A is a subset of B if everything that you see in A you also find in B. So whatever's in the first set also belongs to the second set. Proper subset means not only does everything in the first set belong to the second set, that means it's subsets, but the first set and the second set are not equal, which means the second set by default has at least one more element that A has. It's strictly less than, or B has extra. So looking at number 1 and number 2 here. So A is a set 1, 2, 3. B is a set 2, 3, 1, 4. So the numbers that are in A are 1, 2, and 3. You can also find 1, 2, and 3 inside of set B. So A is a subset of B. Notice that B is not a subset of A because B has an extra element that A doesn't have. So B is not a subset of A, but A is a subset of B. So because B has something extra that A doesn't have, they're not equal sets. So not only is A a subset of B, but A and B are not equal. So we conclude also that A is not only a subset of B, it's also a proper subset of B. So it's actually both. Here, A has the elements A, B, and C. B has the elements A, C, and B. So every element you find in A also belongs to set B. So again, A is a subset of B. But A and B are the actual equal sets. So A is not a proper subset of B because they're equal. So A cannot be a proper subset of B if they are equal to each other. It cannot. A has to be a subset of B and B has to have something extra, which it doesn't in this case. So A is only strictly a subset of B. In fact, B is also a subset of A because everything that you find here, you can also find in there. Just want to point that out. So set A is a set A1, 2, and B. Set B is a set A3, 1, 4, 2, 6. So A, 1, 2, and B. A also belongs in B. 1 also belongs in B. 2 also belongs. I know I don't really write it exactly great, but this is a 6. So element B does not belong in set B. So A is not a subset of B because not everything in A also lives in B. There's this element B that you don't see in set B. That's what this says. So it's not a subset of. And likewise, B is not a subset of A because B has, let's see, A1, 2. Again, B doesn't have little b to go back. 6 doesn't go in here, so you can't go the other way. So for any set, Roman numeral 1 says the empty set is a subset of any set. So by default, every element of the empty set is also an element of another set that's not empty. Or it's empty, doesn't matter. The empty set is a subset of every set. It's a subset of itself. So by default, it says everything in the first set also belongs in the second. But by default, there's nothing that belongs here. So by default, it actually, it fits the description of the definition. And also, every set is a subset of itself. But it's weird that no set is a proper subset of itself because it's equal to itself. Okay, so every set is a subset of itself, and the empty set is a subset of every set. So that's what this says. So you have cardinality now. Cardinality essentially is the number of elements in a set. So for instance, the set with 1, 2, 4, 7, and A has 5 elements, so its cardinality is 5. Over here, this set A has 4 elements, so its cardinality is 4. Set B has 6 elements, so B's cardinality is 6. A's cardinality here is 3. So the number of elements that live in a set is called a cardinality. So talking about subsets, not only are we going to show that one subset is a subset of one set is a subset of another, but we want to actually list all the subsets of a given set and kind of come up with an idea, kind of come up with a formula. So if you take the empty set, the only subset it has is itself, because the empty set is a subset of every set. A set with one element A has the empty set, because again, the empty set is a subset of all of them. So the empty set and the set with A itself. So these two are subsets of the given set. This has a set with A and B in it. So the empty set, then the set with just A in it, the set with just B in it, and the set of itself. So these 4 are subsets of the given set. Now ABC, you look at the set that has nothing. Each set that has only one letter inside. Here's set with A, set with B, set with C. These are subsets. Now 2 elements of the 3 here. So A and B, A and C, B and C. These are all subsets. And now this guy, it's the original, is a subset because every set is a subset of itself. So every set has the empty set and itself as a subset, for sure, at least. Okay. Now A, B, C, D, you look at the set with nothing in it, empty, then the set with one letter in it. Set with A, set with B, set with C, set with D. Then with 2 letters, AB, AC, AD, BC, BD, CD. These are all the subsets that have just 2 elements. The ones that have 3, ABC, ABD, BCD, and ACD. These are the subsets that have 3 elements. And then the original guy, the big guy, is itself. So I want you to notice here, the cardinality of this is 0, but it has 1 subset. The cardinality of this is 1, it has 2 subsets. Cardinality of this set is 2 and has 4 subsets. Cardinality of this is 3 and has 8 subsets. Cardinality is 4 and has 16 subsets. So you understand that the number of subsets is doubling every time I add another element. And now on the right, you see proper subset, they're all proper subsets. The only one that's not a proper subset is itself, because proper subset means it cannot be equal. So these 3 are proper subsets. So you'll never have the original set a proper subset of itself. So there'll always be one less proper subset than the number of subsets. So if there's 1 subset, 0 proper. 2 subsets, 1 of them is proper. 4 subsets, 3 of them are proper. 8 subsets, 7 of them are proper. 16 subsets, 15 will be proper. There's always one less proper subset than the actual number of subsets. Taking this information and changing it to the next page, come up with a little formula here, a little idea. So the number of elements of the first set, 0, 1, 2, 3, and 4. The number of subsets, 1, 2, 4, 8, 16. Notice that they were doubling. So 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, that's 16. As the pattern continues, you keep multiplying by another 2. It'll turn out that the set with A, B, C, D, E actually has 32 subsets, of which only 31 will be proper. It's always one less. So it's always minus 1 of whatever this is. 6 elements, you'll actually double again. So every time you're going down the line, you're doubling. So if you have whatever number of elements you have, whatever the cardinality is, you'll always have 2 raised to that power as a number of subsets. That is fact. So if you have 20 elements, you take 2 to the 20th power, and that tells you how many subsets. The number of proper subsets is always 1 less than the number of subsets. So it's -1. So in general, if a set has n elements in it, it has 2 to the n subsets and 2 to the n minus 1 proper subsets. That is essentially a rule. That is essentially a formula. So a couple of examples here. Find the number of proper subsets of each set. Also find the number of proper subsets of each set. So this set here, A, B, C, D, E, F, G, H, I, J, essentially has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things that live in there. 10 elements. Its cardinality is 10. So the number of subsets would be 2 to that power, 2 to the 10. So 2 to the 10 would be 1024. That's how many subsets. Now, if you actually want to go and list all the subsets, be my guest, but that would be unnecessary here. So out of those 1024 subsets, one less, because the original set cannot be a proper subset of itself. So always subtract 1. So 1023 of those will be proper subsets. Then you have blue, brown, hazel, and green colors of eyes, or whatever you want to call it. There's 4 of them. So the number of subsets that this guy has is 2 to the 4th, or 16 subsets, which means essentially 15 of them would be proper. This guy, 1, 2, 3, triangle, square, stick figure man, and 4. That essentially is 7 elements. So 2 to the 7th is 128 subsets. And then the number of proper subsets will always be 2 to the 7th, or sorry, will be that same answer minus 1, or 127. 128 subsets, 127 of them are proper. The only one that's not proper is itself. So again, no set is a proper subset of itself. Just a little note there. But however, every set is a subset of itself. So no set is a proper subset of itself, but every set is a subset of itself. It's not proper. Okay, so that essentially talks a little bit about set theory. Then we talk about connectors or quantifiers between them, operations between them, essentially. So set union says A union B, that's what little U stands for, union. In fact, I'll put it here. The intersection looks like that. So A union B is the set of all x's such that x belongs to A or x belongs to B, or both at the same time. This one, x belongs to A and x belongs to B at the same time. So intersection would be the set of all elements that they both have in common. This one, as long as one or the other one has it, or possibly both. So this includes the intersection plus extra stuff that one has at the other. So union is like two people that get married. What you bring into the marriage, person A, what the B person brings into the marriage, plus what they have in common what they're having in common bringing into the marriage. This is only essentially what they get together, I guess. So if you take the set 1, 2, 3, 4, 5, take the set 2, 3, 6, 7, 8. A would be the first set, B would be the second set. If you want to union them, it's everything in A or B. So everything in A has to be in the union. So 1, 2, 3, 4, 5. Plus essentially whatever's in B. So you have 2, 3, 6, 7, 8, but you've already accounted for 2 and 3. So you're not going to put them again. That's repeats. So what does B have new that A didn't have? There's also a 6, a 7, and an 8. So the union includes essentially everything, and you don't write the repeats. A intersect B is exactly what they share together. So they have exactly the number 2 and the number 3 in common. That's it. That is their intersection. So if A is a set A, E, I, O, U, and B is a set A, B, C, D, E, the union would be A, E, I, O, U plus whatever the second set B has that wasn't already included in this. So A I already have, B is new, so B, C is new, D is new, E I've already accounted for that. So it's kind of like the sum of like addition, but don't count the repeats. That's the union. Intersection is exactly what they have in common. They have an A in common, and they have an E in common. That's it. That's the intersection. So you talk about a Venn diagram that talks, it's a box that talks about what's called a universal set. A universal set essentially is some kind of set that's referenced. That's kind of like the big guy, kind of like the main set you're talking about. And so you're looking for essentially subsets of it. A Venn diagram better displays it as a box. So if you have only one set, the universal set is the big set and then one set inside of it. A two Venn diagram set has two sets intersecting each other here in the middle. They both live inside the box. Three set Venn diagram has three sets intersected in these positions, in these points. So essentially you have a one set Venn diagram, a two set Venn diagram, and a three set Venn diagram. The universal set is essentially like the big set. It's the one that you're in reference to. So if we look at this example, if the universal set, the main set you're talking about is set 1, 2, 3, 4, 5, and 6. If that essentially is what your focal point is, and set A is 1, 3, and 5, and set B is 2, 4, and 6. Notice that A and B have nothing in common. So I'm going to add this here. Notice that A intersect B is the empty set. Because A and B don't share anything. So when you intersect them, there's nothing in their intersection. This is their intersection. So 1, 3, and 5 belongs to set A, 2, 4, and 6 belongs to set B. U is a set 1, 2, 3, 4, 5, 6. So this box has to have 1, 2, 3, 4, 5, 6. But there's 1, 2, 3, 4, 5, and 6. So this Venn diagram explains this stuff. So A is a subset of the universe, B is a subset of the universe. That's essentially how it goes. So here, just for your knowledge, I'll add this in there. A and B are called disjoint sets. They are disjoint. They have that in common. They're separate from each other. They don't really have anything overlapping. That's the idea of disjoint. Okay, this is a lot of vocabulary. You can go back and refer to the video, practice the notes, the homework, the quizzes. And then now ultimately it's what's called the set complement. The set complement is what's in the universal set, but not in A. So in a one diagram set, if I may, this is set A. Okay. This on the outside of the circle. That is what they call a complement. So a complement essentially is saying what's in the box, but not in the circle. So the circle is A. Outside the circle, inside the box, that's a complement. So let me explain here. If the universal set is A, B, C, D, E, F, G, set A is a set A, C, E. Set B is a set B, C, G. Set C is a set A, G, D, E. A complement is everything in the universe that A doesn't have. So if I may, put it down here. You don't have to do this, but I just want to make a point with the Venn diagram here. A has the set A, C, and E. Okay. The universe also has what? B, D, F, and G that they're not in here. So B, D, F, and G live essentially outside the circle but inside the box. So these four elements are what are in the whole universe that's not in A. That is your complement. B, D, F, G. Okay? Well, I know I'm talking to myself here. B is a set B, C, and G. So B complement is everything in the box minus these three elements. So you take out B and C and you take out G. So the complement of B would be everything else but B, C, and G. So A, D, E, and F. That's complement. The complement of A, G, D, E is essentially A, G, D, E. What does the universe have that C doesn't? B, C, and F. And that's the set complement. This red is an extension of everything we did in the section. So I did one long problem here. It's just so much, I know. But I'm going to walk you through how all this kind of intertwines or how it works together here. So A union, A complement, union B complement. A complement is this set. B complement is this set. If you want to union them, it's everything in the first set, B, D, F, G, plus everything in this set that I have not already talked about, that I have not already included. So A and E. I already have B, D, and F. So everything here plus everything here, and we don't write the repeats. So B complement union C complement. These two. So A, D, E, F plus B and C and F I already have included. So that's the union between the complements. If you want A complement intersect B complement, here's A complement, here's B complement. If you're going to intersect these two sets, essentially it's what they both share. So they both have a D and they both have an F. B complement union C, intersect C complement. These two, what they both share in common, all they share is the letter F. A union B, here's my original A, here's my original B. The union would be everything here, A, C, and E, plus these three, B, C, and G, but I already have C included in the original, so plus B and G. This says A union B complement, or the complement of A union B. This is A union B, A, C, E, B, and G. Complement of this set means what's in the original universe. That doesn't include these guys. So A, C, E, B, and G. A, C, E, B, A, C, E, B, and G. So in the universe, all that's left is D and F. And that's the complement of the union. B union C. B and C. Everything in here plus whatever is in here. So B, C, and G plus A, D, and E, because G is already included there. Now, intersection between B and C. What they share in common, they share the letter G. That's the intersection. Just for your knowledge here, A is here. It's this guy right here. F is an element of A. That's not true. But if I change this to, let's see, not an element of, that would be true because F does not live in A. However, I could say F is an element of A complement. That would be true because A complement is right here. F belongs there, but it doesn't belong in the original set A. D does not belong in the set B. It belongs in its complement, but doesn't belong in the original set. A is not a subset of B because you can't find A or E also in. In other words, Not everything that's in here lives in there. So A is not a subset. B complement intersect with C complement. That's letter G. Is a subset of A complement intersect B complement. A intersect B complement is letter F. So this set that just has F in it is a subset of this set that has D and F. So that's true. The number of elements of set A is 3. The number of subsets that set A has is 8. The number of proper subsets of C, there's 4 elements, so 2 to the 14 minus 1 is 15 sets. And notice, if I take A and I intersect with its complement, if I take what's in the circle and I intersect with what is not in the circle, there's no way in heck they're going to ever have anything in common. So I said earlier, if their intersection is the empty set, they're called disjoint sets. So every set A is disjoint with its complement. So every set, when I intersect it with its complement, will always be the empty set. They'll never have anything in common because the complement is everything that A doesn't have. It's everything else. And A is the complement of the complement. So the complement is kind of like the opposite. That's kind of how it works. So that essentially will put us through 8.1.